Dear friends, this is the lecture number 1 of magnetism and matter. So in this chapter, we'll discuss about magnet. Magnet you all have seen. You always play with that magnet. Also from the childhood, you have been playing with that magnet. Also you keep the magnet in your geometry box, in your bag. Different shape it has. But do you know this magnet first who discovered and who told about this, that it attracts some substances like iron, nickel, cobalt? Do you know this? So when this magnet was first discovered and by whom? Who gave the information about this magnet? One Greek scientist, one Greek philosopher, Thales. Greek philosopher Thales of Miletus. Miletus is a very old town in Greek. Thales is a person of that Miletus city. He first told about this magnet, but its name was not magnet. Its first name was lodestone. Thales told that a lodestone attract iron. The man who first told this in 746 BC. Around 746 BC, this person first gave the information about lodestone. Then its name became magnetite. And now you are telling that one as magnet. So what is this magnet? Magnet is a substance which has attractive property. It attracts some substance which has a repulsive property. Also it repulses some substance, and another one property it has, that is the directive property. The directive property it has means if you hung a magnet by the help of a thread, it always remains in north-south direction, that you have done in the lower classes also. A magnet hung by the help of a thread. And this directive property leads the human society to make magnetic compass. And by the help of the magnetic compass, our ancient peoples, they discovered many lands they discovered inside the sea. Many countries they discovered inside the sea. Also they travel inside the sea by the help of this magnetic needle, or that is called a magnetic compass. So magnet is a substance which has attractive property, repulsive property, as well as directive property. So this is about the magnet, and I told you it was first discovered by, about the magnet first information was given by Thales of Miletus around 746 BC. Then we'll discuss some more important properties of that magnet also. So first, now let's go to the first property. The magnet has two poles, Magnet has two poles. Have you seen any magnet having three poles? Have you seen any magnet having no pole? Have you seen any magnet having one pole? Many questions are coming to mind. So magnet having two poles, very commonly available, also you have seen. Magnet having no pole, I have already told you in the previous chapter about the magnet having no pole. One example I had given. I hope you have remembered that one. That is toroidal solenoid. Toroid is a magnet having no pole. Then magnet having three pole. Yes, it is also possible. If you do faulty magnetization, when you magnetize something, if in a wrong process you will magnetize it, Also magnet having 3 poles are possible. So this is your magnet, you know, one side is should be north pole, one side should be south pole. But in faulty magnetization, sometimes this becomes north and the middle becomes south. Magnet having 3 poles is also possible. But a magnet having 1 pole, have you seen? Have you seen any magnet having 1 pole? That is not at all possible. So the important sentence is monopole doesn't exist. The important sentence is monopole doesn't exist. It is not possible. I think we can make a monopole. Let's try. This is a magnet, suppose having 2 poles. This is a magnet having 2 poles. One side is north pole, one side is south pole. Can you make this magnet having only 1 pole? Let's try. Let's break it. Let's break it from this point. If we break, then what we get? Now we'll get like this. You see? We'll get like this here. 2 pieces. And if you check, this side is north pole, this side is south pole, and here this side will be south and this side will be north. Again, 2 poles will be developed. 2 poles will develop. They will also have the attractive property. Then, so we thought if we cut it from the middle, we will get a magnet having 1 pole, but that's not possible. Again, the part has 2 poles. Let's again cut it. We will again cut this part. Also the same thing will happen. This side will be north, this side will be south, and this side is already south, so this side will be north. The same thing also will happen in this. Means if we cut it and making 2 parts, again 2 poles develops inside the inner part. Again the cutting part again has 2 poles. So we can't make a monopole. Okay, don't lose hope. Let's now keep on cutting like this. Don't lose hope. Keep on cutting like this. We'll cut again small parts, again small part, again small part. After cutting like this, at last you will reach where? You will get an atom. At last you will get one atom which you cannot cut further. Because inside it a nucleus is there which is very hard. Very hard. So you cannot cut. And what about that atom? If you keep on cutting like this, at last you will get an atom. What about that atom? Atom itself is a dipole. You have read in the previous chapter. Revolving electron behaves like a magnetic dipole. You have derived its magnetic dipole moment expression. Mu L is equal to NEH by 4 pi m. Integral multiple of Bohr magneton you have derived. If you want electron revolution around the nucleus, make it a magnet. So there are many electrons are revolving. So the atom itself behaves like a magnetic dipole having 2 poles. So now we'll surrender and we'll agree to this sentence that monopole doesn't exist. Now let's come to the next important property of this magnet. Repulsion is the sure test of magnetization. Repulsion is the sure test of magnetization. Repulsion. Why not attraction? Why only repulsion? Okay. So now I'll give you one substance. I'll give you one substance. So this is one substance. Okay. So I want to know whether this substance is a magnet or magnetic substance. I don't know what is this. So to be confirmed what I did. So now I bring another magnet. So this is a magnet. Okay. So this is a magnet and this is the unknown substance. I don't know what is this. So this substance now get attracted by this magnet. This substance get attracted by this magnet. If attraction, then what happens here? Two possibility arises. What are the two possibility? A may be a magnetic substance. A may be magnetic substance, or A may be a magnet. May be a magnet. If this is North Pole, suppose if it is a magnet, if this will be South Pole, then it get attracted. So then attraction, if attraction happens, there are two possibilities. This may be a magnet, because magnet is also attracted by a magnet. This may be a magnetic substance like iron, nickel, cobalt. Are you sure what is this? Now are you sure what is this? No, not possible. Because attraction can't confirm you whether this is a magnetic substance or this is a magnet. If repulsion happens, then what happens here? If repulsion is there, then it is sure. Two cases arise or only one case. Can you tell that it is a magnetic substance? No, because magnetic substance cannot be repelled. Then what about this? So this is sure a magnet. If repulsion happens, then this is sure it is a magnet. So we'll tell always repulsion is sure test of magnetization. So this is about the second property of the magnet. Now let's come to another one of this magnet. About the third property of the magnet, third important point about the magnet. Let's come to its pole. Magnet has two poles. One is a north pole and one is a south pole. But where these two poles actually present? Where the two poles actually present? You will see. So this you know, the two poles of the magnet not present completely at the end of the geometrical structure. Rather, they present little inside. So this length, this length, this is called magnetic length. Poles present little inside, not completely at the end, but this length, this is called geometrical length, or this is also called as physical length. Physical or geometrical length. Then, are you thinking to bring this pole completely to the end? Okay, if you are thinking like this, then this type of thinking must come into your mind that, sir, please, you caught the magnet from here. You caught the magnet from this portion. You caught the magnet and threw it. So now the pole is coming to the end. No, this doesn't happen. If you do this type of experiment, you can able to see. If you caught the magnet from here, again this pole will sit inside. Again this pole will sit inside. If you again caught it, again the pole will sit inside. So the magnetic poles always present little inside the end of the magnet. And then the question is coming to your mind, is there any particular position of the pole? Is there a relation between this magnetic length and geometric length? Yes, there is one relation. Magnetic length is equal to 7 by 8 into geometric length. 7 by 8 into geometric length. There is one relation which is experimentally found, that magnetic length is 7 by 8 into geometric length. But this 7 by 8 number in some books will find 6 by 7. As this is an experimental fact, so it's not sure. Maybe 6 by 7, maybe 7 by 8. So this is the relation between magnetic length and geometric length. So how will you know that the pole is present there? In that region, the attraction is maximum. The the attraction is maximum at the region of the pole. So that indicates the pole is present there. Okay, so this is about the pole. So now we'll come to some important points about this magnet. First is some important quantity about this magnet. First is pole strength. Pole strength. So this is the main hero of this chapter. Electrostatic chapter. You all have read. Who is the hero of electrostatic chapter? That is charge. Charge is the hero of the electrostatic chapter. So charge symbol you have written small q. Similarly, pole strength is a hero of this chapter. What do you mean by pole strength? Pole has the ability to attract or to repel, but what is pole strength? Pole strength means it is also the ability, the strength which will measure quantitatively. Which will measure quantitatively pole attract or repel. But how much attract, how much repel, that quantitative idea, quantitative calculation that will get from the pole strength. So it's a quantity of this chapter, just like the charge in electrostatics. And its symbol will write Qm. So this is the pole strength symbol Qm. Q you have written for charge in electrostatics. I am writing here Qm. This is the pole strength. The strength of the pole, the attraction or repulsion strength of the pole is called as pole strength. Then what is its SI unit? Its SI unit is ampere meter. Ampere meter is its SI unit. And what is its CGS unit? Ab ampere into centimeter is the CGS unit. Ab ampere, as magnetism is going on, so we will write only electromagnetic unit, EMU. So ab ampere into centimeter. Then what is the dimensional formula? Very simple. Ampere A1 and meter is L1. So this is about the pole strength. But positive charge and negative charge you heard in the first chapter. Charges two types, positive and negative. Similarly, poles two types, north and south pole. If you compare them, north pole just play the role of positive charge. South pole just play the role of negative charge. So north pole whenever we'll write by the symbol plus Qm. South pole whenever we'll write the symbol by the minus Qm. Just only to differentiate them, there is no other meaning. Don't think that a plus and a minus sign are less or more. They just indicate they are opposite poles. Just like a plus Q charge and a minus Q charge. So if I draw a magnet here, if this is north pole, if this is south pole, I can write this is plus Qm and this one is minus Qm. So this is about the magnetic pole. Then another important thing also I am telling about pole. If we caught a magnet, another important property of this pole I am telling you. Suppose we caught a magnet, we caught a bar magnet. This is a bar magnet. We caught this bar magnet perpendicular to its length. Perpendicular to its length, we caught it like this. So this is the plus Qm and this is minus Qm, two poles are here. We caught it like this, so we will get the pieces in this way. We will get the pieces in this way. We will get the pieces. It converts into two pieces, and each piece having two poles. What happens to the pole strength? That question is coming to your mind. What happens to the pole strength? Pole strength remains unchanged. Pole strength remains here unchanged. So this becomes minus 12. No change in pole strength. These are the experimental facts. If we got a magnet perpendicular to its length, the pole strength remains unchanged. There is no change in pole strength. Now let's come and see. If we got a magnet, if we got the magnet along its length. This is the magnet. You cut it along its length like this. If you cut it along its length, so this was plus QM, this was minus QM. Now you cut along its length, then what happened? You will get two magnets. You will get two magnets here. And I cut it in such a way that they become half-half. The area of cross section of the magnet become half-half. Then what happens here? If half-half, then the pole strength becomes half. Here also pole strength becomes half. Minus Qm by 2, minus Qm by 2. So if you cut a magnet along its length in two equal parts, then pole strength becomes a half. You remember this fact, which will help you to solve some numericals, which concept will help you to solve some questions. If we cut a magnet perpendicular to the length, there is no change in pole strength. But if we cut a magnet along the length, then pole strength becomes a half if you cut it in two equal parts. So this is the pole strength of the magnet. So now we come, after getting the information about pole strength, now we'll come to the next law, what we have done also in electrostatics, because this chapter is just a copy of electrostatics chapter. Those who have understood the first chapter electrostatics, they can also understand this chapter clearly, because everything is just a copy of electrostatics chapter. So next we come to that famous law what you have read in electrostatics chapter. The same scientist, same law, only different is charge will be replaced by the pole strength. So what is that law? You all have remembered that law. That is nothing but Coulomb's law in magnetism. That was Coulomb's law in electrostatics. So what is Coulomb's law in magnetism? The same law. The magnetostatic force between two poles is directly proportional to the product of their pole strength, magnitude of a pole strength, the product of magnitude of a pole strength and distance of, and inversely proportional to square of distance of separation between them. So this is equal to K Qm into Qm. I can write Qm dash. If one is like north pole, one I can write south pole, divided by, this is R square. R square. So this is K, but in place of K, what I write? There what we had written in place of K? K was 4 pi epsilon naught if the medium is air. Similarly also we will replace here K by mu naught by 4 pi, what you have already done in the electromagnetism chapter, and this value also you know, 10 to the power minus 7 in SI unit. So Qm dash divided by R square, and this is if the medium is air medium and SI system. SI system and air medium, then this is your Coulomb's force. F is equal to mu naught by 4 pi Q dash divided by R square. So this is about the Coulomb's law in magnetism, just similar to your electrostatics Coulomb's law. So now we will come to the just similar field. Just similar field also. There you know about the field, that is the electric field. Here also the similar field is called magnetic field. The similar field is called magnetic field. What is magnetic field? Magnetic field means the same definition. The region around a magnet. The region around a magnet within which its force can be realized by other magnets or magnetic substances. The region around a magnet within which its force can be realized by other magnets or magnetic substances, that is the magnetic field. and magnetic field will be measured by magnetic field intensity or magnetic field strength. Magnetic field intensity or strength, the symbol will write here H or B, magnetic field intensity or magnetic field strength. And what will the definition of this magnetic field strength or magnetic field intensity? What is the definition of this? Similar definition again, just like electrostatics. It is nothing but the force experienced by unit test pole. You have done in electrostatics unit positive charge. Test charge you had taken in electrostatics. Here also we will take a test pole. Test pole means unit. Their unit positive charge. So your unit positive charge here is just replaced by unit north pole. Unit north pole. Okay. So this is the unit north pole, or this is called as test pole. This is called as test pole, as this is called a test charge. Similar definition. At any point, if you want to find the magnetic field strength, the force experienced by unit north pole or test pole placed at that point. Placed at that point. But the question is now coming to your mind. Just before I told you, monopole doesn't exist. But now I am telling you, force experienced by one unit north pole. But how, from where a single north pole will come? It's not practically possible. This is only the theoretical definition. Just like the electrostatics we are writing here, but this is not practically possible. So this is force experienced for unit test pole. I wrote the test pole symbol as QM naught. This is the ratio of, or this is the force experienced by unit north pole. And if you put the force formula here, mu naught by 4 pi or K. This is QM naught. If we are finding the pole strength due to single pole, this pole is applying force and this pole is experiencing force. The test pole, its effect is negligible, just like the test charge. So this is R square divided by again QM naught. If QM naught cancel, so you are getting the answer. You can write H or you can write B, no problem. So mu naught by 4 pi QM by R square. So this is the magnetic field intensity due to a single pole. Magnetic field intensity. But where is the direction of this magnetic field intensity? Again, compare to the electrostatics direction of the magnetic field. There it was away from positive charge. You remember? Electric field direction was away from positive charge. But here magnetic field direction is away from. Similarly, you tell me now, you think of the answer, away from positive charge. So this is away from, okay, you are thinking the right answer, north pole. So it is away from north pole and there it was towards negative charge. Away from positive charge towards negative charge. So this is also similarly towards which pole? South pole. So this is the direction of the magnetic field intensity. Away from north pole and towards the south pole. Always the magnetic field intensity direction is like this. That means from north to south. Very clear. From north to south. Always the direction. As your electric field direction was from positive charge to negative charge. So this is about the magnetic field strength and is measured by the unit you know, Tesla. You have already done in electromagnetism chapter, and the simplest unit is Gauss. So next we come to magnetic field lines. Again, magnetic field lines. Magnetic field lines. Field lines. Now you are thinking, again sir will compare this magnetic field line with electric field line. Yes. Yes. And if you don't know electric field line, what is electric field line? You go back and see the previous video of the, not just previous, you see the video of the electrostatics chapter. What is electric field line? You listen that, you try to understand, then after that you can able to understand what is magnetic field line. If you understand the first chapter, the first portion about this Coulomb's law, electric field line, electric dipole, also this chapter you can able to understand within a few minutes. So this is magnetic field line. Again the same thing, imaginary lines, path followed by unit test pole, unit north pole. When it is free to do so, magnetic field lines. In practical lab, generally we draw the magnetic field lines, but while drawing magnetic field lines in practical lab, are you taking unit north pole? No, because that is not practically possible. So in practical lab, when you draw the magnetic field lines, what you take? A magnetic compass you take. You take a magnetic compass and you draw the magnetic field lines in the practical lab. So this is about the magnetic field line, the imaginary lines which are nothing but the path followed by unit north pole when it is free to do so. If we draw the magnetic field lines for a bar magnet, this is north pole, this is south pole. I told you magnetic lines forces moves from north pole to south pole, and that happens outside the magnet. Remember, that happens outside the magnet. But important difference here is electric field lines of force start from positive charge and end at a negative charge. Electric field lines start from positive charge and end at negative charge. They go and end here. But magnetic field lines from north pole to it go to south pole outside the magnet, and inside the magnet again it move from north pole to south pole inside the magnet. So what difference you mark between electric field line and magnetic field line? First difference, this magnetic field line for a closed loop, this is called loop, but the electric field line cannot form a loop. It cannot form a loop. You can't say this as a loop, because loop, that one is only called as a loop which move in this direction and come in this direction and again now become closed. This is called loop. But if it is going like this and this, it cannot be called as a loop. It is like this, but it is like this. So this is about this is the magnetic lines of force. How it form closed loop. Okay. So if you draw other lines of forces also, they will come like this. They will come like this and pass and close here. And many lines also, it will from this, and also it pass from north pole, from south pole to north pole inside the magnet. If you draw magnetic lines of forces, also many poles lines of forces will come like this. You can draw the magnetic lines of forces for a bar magnet. But the basic difference between them you understood. Magnetic lines of forces can form closed loop, but electric lines of forces cannot form closed loop. Another difference also you mark here. Another difference. What is that difference? Electric lines of forces never passes through a metal. Electric lines of forces never passes through a metal. When metal comes, electric lines of force block there on the surface of the metal. It cannot penetrate. But magnetic lines of force can pass through a metal. This is another difference. But all other properties of electric lines of force are also valid for magnetic lines of force. What property you know in the first chapter? That the tangent drawn at any point provide the direction of electric field intensity. Here tangent drawn provide the direction of magnetic field intensity. Two magnetic lines of force cannot cross each other. The region where magnetic lines of forces are crowded, field intensity is more. So all these properties what you have read in electric lines of force, they are also valid for magnetic field lines or magnetic lines of force. Then we will come to magnetic dipole. Magnetic dipole. So after listening all these, I think you are feeling just the revision of the first chapter. You are thinking, sir is doing the revision of a first chapter. Yes, just revision of a first chapter. Similar portion, what is the behavior, what quantities are there in the electrostatic, the same thing also there here in the magnetostatics. So magnetic dipole, again you are thinking, sir I will tell about electric dipole. Yes, electric dipole, that is positive charge. Electric dipole has positive charge and negative charge. Similarly, this magnetic dipole, I am doing the one side is better. I am doing one side your electric dipole and one side I am doing electric dipole here, and one side I am writing magnetic dipole. Magnetic dipole. So electric dipole, it consists of two charges. One is plus Q, one is a minus Q. Plus Q, minus Q. Here also similarly two poles. One is north pole and one is a south pole. And electric dipole, practically where it is available, I have told you, one molecule is a dipole. Like water, it's a electric dipole. Magnetic dipole, but you all have seen in your naked eye. You all have seen this magnetic dipole in your day-to-day life. Common man has seen this magnetic dipole. What? Bar magnet which you are keeping in your school bag. The bar magnet is a magnetic dipole. Or any magnet having two poles separated by some distance, that is a magnetic dipole. So in dipole, to know the strength of the dipole, you have read one quantity, that is dipole moment. Dipole moment is, your electric dipole moment is Q into 12. Similarly, if I tell you this is the length, 12 is the length of this magnetic length, but we have to consider 12 is the magnetic length. If the question is coming 12 is geometric or magnetic length, this is the magnetic length. So what is the dipole moment, and symbol is what? Symbol is capital M. So capital M is equal to Qm. This is plus Qm and this is minus Qm, to equal and opposite poles. Okay, so Qm into 12. So this is magnetic dipole moment. Electric dipole moment, magnetic dipole moment. Is it a vector? Yes. Is it a vector? Yes. Where is its direction? Its direction was where? From negative to positive. Dipole moment direction is from negative to positive. This is by convention. Don't ask me why. From where I got this information. This is just by convention. Everybody just has taken this, that from minus Q to plus Q. And here, similarly, the dipole moment will be from south pole to north pole. From south pole to north pole, this is the magnetic dipole moment. Just opposite to it. From south pole to north pole. So this is about the magnetic dipole moment and electric dipole moment. So unit, okay, unit, I left the unit here. If we tell unit, what happens? Coulomb into meter. This Coulomb into meter, and here the unit is what? Here the unit will light. So this is the unit will light. This QM unit is ampere into meter. So it becomes ampere meter square. So electric dipole moment unit is Coulomb into meter. Magnetic dipole moment unit is ampere into meter square. But I want to share you one important information here. This unit is actually brought from where? So you just recall this structure. That when one electron revolves around the nucleus, it behaves like a magnet. Or a coil carrying loop behaves like a magnet. Current carrying loop is also a magnetic dipole. You have done this proof in the previous chapter. Current carrying loop is a magnetic dipole. When electron revolves around the nucleus, also it is a magnetic dipole because that is also loop. So here I current first. So it has some radius. Here what was the dipole moment? Dipole moment formula was Nia. Nia, N-I-A. So from here actually this unit come. I is ampere, A is meter square, so it become ampere meter square. Ampere meter square. So now this is about the magnetic dipole. And in dipole also some things we can compare. Some more things also we can compare here. You see what we can compare here about E axial. E axial. What is the formula? 1 by 4 pi epsilon naught 2p by r cube. Here also we write B axial magnetic field along the axial line mu naught by 4 pi. This is 2m by r cube. What is r? You know, if this is a point from the center, this distance is r. Similarly, from the center, if you take a point P here, this distance is r. So similarly, so this is the direction also same. This direction is along the dipole moment, and here also the direction will be along the dipole moment. And then come to the E equatorial. E equatorial was 1 by 4 pi epsilon naught. This is P by r cube, just it's a half. So here B equatorial is mu naught by 4 pi. This is A by r cube. This is B equatorial. And what about the direction? This is opposite to dipole moment. If you have remembered, opposite to dipole moment is a direction, and its direction is also opposite to dipole moment. Then come to now the torque. When this dipole, electric dipole, is kept in uniform electric field, it experiences torque. What torque it experiences? Tau is equal to P is sin theta. So the same thing, the same torque, if we keep a bar magnet in a uniform magnetic field, it also experiences the same torque, mb sin theta. mb sin theta, same torque. And the derivations if you want to do for these three, for this similar to this. Only if you have done these derivations, I have done these derivations in the video of the first chapter of your 12th class. Just you will replace in that derivation as where there is plus q charge, you just replace that one by plus qm. Where there is minus q charge, replace by that one minus qm. Then where there is p, you replace that by m. Where there is e, you replace by that by b. And you just copy that derivation, everything will be same. You will get all these expressions. Then it will come, what is the work done to rotate the dipole? If you have remembered, there is also the work done to rotate the dipole. So how much work is done to rotate the dipole? So W is equal to, I am writing here, Pe cos theta 1 minus cos theta 2. Now come to the work done to rotate. P is m, E is B. So again this is cos theta 1 minus cos theta 2. If we come to potential energy of this, minus P cos theta. If we come to potential energy of this is electric potential energy, but this is magnetic, minus MB cos theta. These derivations also similar, same thing, everything is same, just you can copy it from the electrostatics if you want to do these derivations. So this is about the different quantities which are similar to electrostatics chapter. So we discussed a lot, we discussed now many portion of this chapter, a major portion of this chapter just comparing with electrostatic. So let's do one important question which always comes in exam. You have also done this question in electrostatics chapter. Question is like this. Calculate the work done to rotate a magnetic dipole in uniform magnetic field from stable equilibrium position to unstable equilibrium position. If you want to note down this one, you can note down, no problem. Calculate the work done to rotate a magnetic dipole in uniform magnetic field from stable equilibrium position to unstable equilibrium position. Dipole moment capital M and magnetic field strength capital B is given to you. You can do this question, but always I am telling, now you pause the video here, use the formula, try this question, and after completing this question again you play the video so that your creativity will increase. Don't continue watching like this. So now you pause the video here. Okay, I am telling you this answer. So you know equilibrium part, stable equilibrium, unstable equilibrium, both are also similar. Stable equilibrium, theta is equal to 0. Unstable equilibrium, theta is equal to 180. If this is theta 1, this is theta 2. From stable equilibrium we will rotate to unstable equilibrium. So what is the work done? Just before I wrote this formula, MB cos theta 1 minus cos theta 2. So MB, so this is cos 0 minus cos 180. But cos 180 is, this is minus 1. So it become now 2MB. So this is the famous answer. Always comes in exam. Also many times it comes in board examinations. Another question also I want to do here. I hope this question is correct. You all have done this question correctly. Okay, it's good. So now I will come to the next part. Next question. Another question I am doing here. A bar magnet of magnetic moment M. A bar magnet of magnetic moment M is bent in the form of a semicircle. It's bent in the form of a semicircle. What is the new magnetic moment? This is the question. Again I am repeating. A bar magnet of magnetic moment capital M is bent in the form of a semicircle. What is the new magnetic moment? Pause the video here. Okay. So now I am telling you the answer. When? How it's bent in the form of semicircle? Now let's draw the figure. So this is the figure. Bar magnet is bent in the form of semicircle. The pole strength is plus Qm. Here is minus Qm. So here is plus Qm. Here is minus Qm. So this length is 12. If this length is 12, then this whole length is also 12. This whole length is also 12. Okay. But the distance between the poles is here 12. But here the distance between the poles is not 12 now. The distance between the poles now changes to 2r. 2r, the distance between the poles. That is equal to diameter. Diameter of the semicircle. Okay, so this one is given to you. M is equal to Qm into 12. But this one, M dash is equal to Qm into 2r. But we don't know 2r. We don't know 2r. Let's bring a relation between 2r and 12. R and L, let's bring a relation. This is half circumference. So can I write 12 is equal to pi r? As this is half circumference, I can write 12 is equal to pi r. Then r is equal to 12 by pi. Now you write the new magnetic moment is Qm into 2r. Qm into 2r is the separation between them. So Qm into 2, then r is 12 by pi. But Qm into 12, this is nothing but capital M. So this is 2 by pi capital M. So this is the new magnetic moment. M dash is equal to 2 by pi into capital M. I hope your answer was correct. Okay. So now I am going to do another question. Another question I am coming to you. Two magnets are kept like this. This is one magnet. This is one magnet. Two magnets are kept like this. This is the north pole and this is the south pole. Here it is a north pole and this is the south pole. So two magnets, they are the equal magnets. Same dipole means pole strength is same. Pole strength in both dipoles are same. Of all poles, there you can able to see 4 poles are there, but 2 poles icon side here. Okay. So magnets are kept like this. My question is, if each magnet has magnetic moment M, what is the magnetic moment of this configuration now? What is the magnetic moment of this configuration now if each magnet has magnetic moment capital M? Pause the video here. Do this question. Find the answer. After that, you play the video. Okay. So, I am telling you the answer. Now, this is one magnet. Where is its magnetic moment? So, its magnetic dipole moment is here in this direction. Its magnetic dipole moment is here in this direction. So, these are the two now dipole moments direction. We can do this question in 2 ways. From the two dipole moments, we can find the new dipole moment, or also we can do by the configuration also we can find. You see, when they combine, by 2 methods I can do, but I am doing the simple one. You see, when they combine, now these 2 poles neutralize each other, only these 2 poles remain. And what is the distance between them? You see, what is the distance between them? Between them now the distance is this much. So if this is the magnetic moment of each magnet, M is equal to Qm into 12. Length of each magnet I am taking always 12. That is M is equal to Qm into 12. But this is the magnetic moment of each magnet. But what is now the magnetic moment? Now the distance change. If this is 12 and this is 12, this is the hypotenuse, it becomes root 2 into 12. Root 2 into 12. Now the distance between the poles changed. So Qm root 2 into 12. Okay. So now it becomes root 2 Qm into 12. So Qm into 12 is what? Magnetic moment of each magnet. So this is the answer. I hope you could able to do this answer correctly. I am now going again to the next question. Next question is like this. A bar magnet of magnetic dipole moment M. Magnetic dipole moment M is kept like this. It has 2 bits. First bit, you cut the magnet in 2 equal parts perpendicular to length, and bit B is along length. In 2 equal parts perpendicular to length and along length. What is the new magnetic moment? What is the new magnetic moment now? In this case, you see what happens here. New magnetic moment of each part. Now first come. Again I am repeating the question. A bar magnet of magnetic moment capital M is cut into 2 equal parts along its length, perpendicular to length, along its length. What is the magnetic moment of each part? Pause the video here, do this question, and after completing the answer, now again you play the video. Okay, I am telling you the answer. Perpendicular to length. So what change? Perpendicular to length means it's like this. I have told you earlier, if you cut it like this, perpendicular to length, pole strength never changes. But what change here? The separation between the poles now change, because initial separation was suppose 12. Now the separation become L. So what was the original magnetic moment? Qm into 12. What is now the magnetic moment? M dash. The pole strength never changed, but the distance changed. Distance become half. That whole distance 2L now become half, it become L length only. So 2L by 2 become half. And what is this? This is M. So magnetic dipole moment becomes a half if we cut it like this. But if we cut along its length, then what happens you see? Along its length. So if along its length means it is like this. It is like this. In two equal parts. What about the pole strength? Pole strength Qm dash is equal to Qm by 2. I have told you, if we cut along its length, then pole strength becomes half. So new magnetic moment now M dash is equal to, so this is the original magnetic moment, Qm by 2. But the length remains intact. Length is 12. So Qm into 12, this one M, so M by 2. So what is your conclusion? So your conclusion is, when you cut a magnet, may be perpendicular to length, may be along the length, if two equal parts, then magnetic moment always becomes a half. Always becomes a half, the magnetic moment. Another question I want to do here. Another important question I want to do here. So I hope the previous question, this answer was correct. You all have done correctly. So if one magnet is here and one magnet is here, two magnets are here, each having dipole moment L and M. So here is the north pole, here is the south pole, and here is also north pole, or I am writing here south pole, here north pole, no problem. Anywhere you can do the poles, no problem. So this distances are same, this is D and this is D. You have to find out the magnetic field at this point. If you want to find magnetic field at this point, then how can you find? Magnetic field intensities, this is the question. To find at this point, this is D, this is M, this is M. How will find magnetic field intensity both in magnitude and direction? That's the question. You pause the video here, do this question. After getting answer, again you play it. So now you pause the video here. Okay, I'm doing the answer. See, so this point is which line? This line is the which line of this magnetic dipole? Axial or equatorial? So this is equatorial line, and this is also formed by this magnet, also this is equatorial line. Let's take it as 1, let's take it as 2. So write the magnetic field first due to 1, B1, mu naught by 4 pi M by D cube. This is the formula for equatorial line. But where is the direction? The dipole moment is from south to north, and in equatorial line the magnetic field and dipole moment are making 180 degree angle, means opposite to each other. So its magnetic field will be in this direction. So this is B1. Then come to B2, this due to this one. So magnitude is the same, mu naught by 4 pi 2m by d cube, because m, d, everything is same. So this dipole moment is in this direction. So where is the magnetic field? Just opposite to this dipole moment. I am showing it here. This is the dipole moment. So it's just opposite to it. So here. So this is B2. So B1, B2 are perpendicular to each other. So net magnetic field is B1 square plus B2 square root over. As both are same, so simple root 2 into mu naught by 4 pi 2m by d cube. This is the net magnetic field due to both. But where is the direction of the magnetic field? As per which law? By which law we will get the direction? We will draw the resultant. By which law we will draw the resultant magnetic field? You just go to the vector. Which law is applied here? Triangular law or parallelogram law? Okay, so you are thinking, sir, please don't recall us those laws. Okay, so already you know everything. This is by parallelogram law. This is the resultant. This is the resultant magnetic field. If this is B1 vector, so this is the resultant magnetic field, that is B vector. So what is the angle? Angle you can find theta. So tan theta is equal to B2 by B1 or B1 by B2, no problem. So it is coming 1 because both are same. So theta is 45 degree with any one magnetic field, or you can show the direction in figure also. So this is one important question, sometimes also comes in exams. So today I discussed about the magnet, the important quantities comparing with electrostatics, and also I discussed some questions. Thank you.